Hello class, this video is on Venn diagrams and truth functions. We've been understanding complex sentences like P and Q as a string of symbols. It turns out that you can actually understand the exact same thing as a kind of picture. Here's our warm-up to see how this is going to work. Take a bunch of objects like this array of Lego minifigures. If I wanted to isolate my favorite minifigures, what I could do is draw a circle around them. So I might say, look, this circle is my circle of favorite minifigures, and everyone in here is one of my favorites. Then you might also have a circle that you could draw around all of your favorite minifigures. Now, some of our minifigures are in both of our circles. These are the points or the minifigures that are both of our favorites, like that Captain and Chewbacca. Some of the minifigures are just your favorites, and some of them are just my favorites, and some of them are neither of our favorites. So there's 4 different regions of space here that we can delineate by drawing circles, and the things that we're drawing circles around are little points. Now in this case they're minifigures, but we could also understand them as points in space. So the circle around here is a bunch of points in space, and you can think of the things in this circle as the points at which the sentence P is true. So being inside the P circle means the sentence P is true. Being inside the Q circle are all the points at which the sentence Q is true. If you're in both circles, then that's where the sentences P and Q are both true. And if you're outside them both, that's where both of those sentences are false. Notice then, understood in that way, each region of the diagram corresponds to exactly one region of our truth table. Row 1 is where both of the atomic sentences are true, so that corresponds to the region in the middle, the intersection of P and Q. Row 2 is where you're just in the circle P because only P is true, so that would be this half moon shape over here. Region 3 would be this moon shape over here with Q, and finally region 4 would be the empty space at which you're outside both of the circles. In a Venn diagram with 2 atomic sentence letters, there's always going to be exactly 4 regions. That's exactly like a truth table. When you have 3 atomic sentences in a Venn diagram, you're going to have 8 regions of the diagram, and guess what? You have exactly 8 rows of a truth table. The Venn diagram and the truth table, in a sense, do the exact same thing. We'll look at the 3 case later. Let's first look at the 2 case. Remember, there's 2 systems of codes that we're going to need to follow. Being true for an atomic sentence means being inside the circle, and being true for the output sentence means we're going to shade it. So we're going to use the convention that shaded means true, and that way we can give a representation of this diagram. We can give a representation of this sentence as a diagram. This sentence is true. It's a truth function that's true on exactly 1 row, so we need to shade the corresponding region, so that would just mean we shade region 1, and it would look like this. So this diagram encodes the exact same information as this string of symbols considered as a sentence. Consider a different one. So here's one more example. Think of disjunction. So I switched to the example. This sentence is now true on 3 separate rows. So we need to shade regions 1, 2, and 3. Now this is a picture, in a sense, of disjunction. That's what the picture looks like for disjunction, where all the rows on which the sentence is true, the regions corresponding to them are shaded in our Venn diagram. If you think you've gotten the idea, then consider this sentence and see if you can figure it out. So I can give you a sentence now, and you can give me back a picture that is the encoding of all the information that that string of symbols represents. Okay, I really mean you need to stop your videos and work this out. So see if you can do the exercise that we just did. I'm going to show you the answer in a second, so if you don't pause your videos now, you're not going to get the chance to work on it. Here it is. This is what we're going to do. The first thing you need to do is construct the truth table. So I inverted Q, FT, FT. I then took the disjunction of that with P, and I got TT, FT. Then I inverted that and got FFTF. So only region 3, row 3 is the only place it's true, so I shaded region 3. So this is my P, this is my Q. There's a quick little picture of that sentence. Now, if you think you've got that, then you should be able to figure out how to do 3 sentences without me even explaining it to you. So consider this sentence, P and not Q or R. See if you could give me a Venn diagram representing that, and let's use the following way of doing the Venn diagram, where let's do this circle is P, this circle is Q, this circle is R. See if you can figure out what each of those regions represents, compute the truth function, and shade the diagram, and then we'll compare our answers. Okay, last chance is to stop your videos and see if you can figure it out. So this is what I did. First, I made my atomic sentences P, Q, and R and 8 rows of my truth table, and now I need to figure out how those correspond to the regions of my diagram. Well, region 1 is where P, Q, and R are all true. That's always going to be the innermost region where all of your circles intersect. So this is region 1. Similarly, region 8 will be always the negative space, where all the bottom row of any truth table will be where all the atomic sentences are false. That will always be the empty space out here, in which case that's number 8. Row 2, this is where you're in P and Q, but not R, so this is the little point up here, the intersection of the top two circles. Row 3 is you're in P and R, so that's why it's over here. You can quickly work out for the rest and see if that corresponds to the way you did it on your paper. Now all we need to do is compute the truth function. When I did that, I got T only on row 4. So lastly, we need to translate that into our diagram and just shade region 4 and nothing else. It looks like this. So here is the picture that represents that sentence. Now, in order for this trick to work, we must be able to have a Venn diagram for any arbitrary number of circles, because we can have complex sentences with any number of atomic sentences as constituents. There's no limit on the complexity of the kinds of sentences that we can construct. But if you try to think about how to do a Venn diagram for four letters, you'll quickly convince yourself that it's very difficult. Well, people have figured this out. There's a way to do it with spheres. It's quite elegant. So this diagram actually shows you at different levels of focus all the different regions. The red is the regions that they're showing you. So what it is it's a complete sphere with 4 inner spheres. Those 4 inner spheres are the 4 atomic sentences. This outer sphere, so this is the negative space. This would be row 16 of the truth table. Then these spaces, these are the regions where you're in only one sphere alone. So this would be 4 separate regions here. It's a little hard to see in that picture. This would be the intersection where you're in exactly 2 spheres. I think there's 6 of these. This is where you're in 3 spheres, and then this is the innermost region. This is the top row of your truth table when you're in every one of the intersecting spheres. So there are ways of doing it with 4. I will not make you do this on the test. I couldn't even draw this thing, let alone shade it properly. If you want to do it with 5 sentences, you can use ellipses, and this is quite elegant. So here's a symmetric and beautiful way of doing a Venn diagram for 5 sentences. That was not Venn's original method. Venn used the 3 original circles, and then he started drawing rainbow shapes for the other ones. So this is the way Venn did it. This is an original style Venn diagram for 5 sentences. So the 3 circles are the first 3. This red is the 4th, and this green is the 5th. Venn did show that you can keep adding more little snaky things to this rainbow and do this for any arbitrary number. On the exam, you're just going to be responsible for doing them with 2 and 3 atomic sentences. That's not all you need to be able to do with Venn diagrams. There's one more concept. Because if Venn diagrams can encode truth functions, then they can encode logical validity too. Why? Because we can understand logical validity as relations among truth values of premises and conclusions. We're going to do this just with a simple argument form where you have exactly one premise and a conclusion. This horizontal bar still means our therefore line. So the thing above it is my premise sentence. The thing below it is my conclusion sentence. These are just sentences so we can represent with Venn diagrams. And then if you think about it, you can decide how this diagram must look in order for the inference to be valid. So see if you can figure it out. Pause your videos and decide if this argument is valid or not and why. And then I'll explain to you the way to think about it so you can see if you got it figured out on your own. Okay, last chance to pause your videos. This is not easy to figure it out first on your own. It's actually counterintuitive. So the vast majority of people think of it the wrong way. But once I explain it to you, and once you see a couple of them, you'll get the trick. See, it looks like this is invalid because there's a region where it's blank up here, but it's shaded down here. So it looks like we could go from false to true or something, and that makes it invalid. But that's actually not the right way to think about it. The validity says if the premise is true, then the conclusion must be true too. So all that matters for validity are regions where the premise is shaded. You disregard all the regions where it's not shaded. So think about the premise. It's shaded in 3 regions. That's where it's true. In order for the argument to be valid, my conclusion must be shaded in those 3 regions as well. It could also be shaded elsewhere. That doesn't matter. All that matters is that it's shaded everywhere that my premise is shaded. So this argument actually is valid. Okay, let's do one more. Pause your videos and see if you think this argument is valid or not. Okay, last chance to pause your videos. It turns out this argument is invalid. Why? See, again, you might think it's valid because this one totally covers that one, but that's not the right way to think about it. If the premise is shaded, is the conclusion shaded too? Well, it is in these 2 regions, but not in this region. If you could be true in the premise, but false in the conclusion, that's invalidity. That's a counterexample. So actually, this region right here is our counterexample region. Notice the special cases of Valid arguments, those three weird cases apply here too. If an argument is circular, that means the premise and the conclusion are the same. That means the two Venn diagrams are the same. So there's going to be no counterexample region. Wherever the premise is shaded, the conclusion would be shaded too. Or another weird case of validity, a logically true conclusion. Notice this is shaded everywhere. This is what a diagram of a tautology looks like. There's going to be no counterexamples to this. Whenever any premise is shaded, it doesn't matter how it's shaded, the conclusion will be shaded there too because the conclusion is shaded everywhere. Finally, the weird case of validity, number 3, contradictory premises. Well, that will not be shaded anywhere, so there will be no counterexample rows. So we have two different skills with Venn diagrams. One is I can give you a sentence and you can give me back the diagram. And skill number 2, I give you an argument represented in visual form and you tell me if the argument is valid or not. Okay, thanks.